All right. Okay, so uh, so far we have seen what's the one form. One form was an object which eats vectors, right, and gives us numbers. Now, geometrically, one forms corresponds to what? A linear combination of lengths of signed lengths of projections of vectors to the coordinate axis. You take its projection to the coordinate axis, you get three vectors on the coordinate axis. You measure the signed length. What I mean by signed length, of course, with points, in the positive direction or negative direction. So you assign, you get a sign, and then you take a linear combination. That's a one form, right? So one form, has the form. So this a one form, okay? Something like this, right? Let's say some function dx plus another function dy, and then hx or dx1, dx2, dx3. You'll see two forms. Two forms are actually something you already know. Geometrically, it measures signed areas, okay? And you have known one concept from linear algebra, which tells you the shape of a, the area of a parallelogram spanned by two vectors. So if I give you two vectors like this, right, they span a parallelogram. How would you calculate the area of this? Sorry? The determinant, right? You take these two areas, put inside a matrix, take its determinant. Determinant is a real number. It can be positive or negative. Therefore, it's the signed area. If you take the absolute value, you get the area. So two forms objects like that, they measure given in this on the parallelograms areas and multiply them with some constants like this. Okay. So let me start. Okay, consider the parallelogram formed by two vectors. Let's say V, A, B, and U, C, D. Okay, like this. U and V. Okay. The area of the parallelogram is given as the absolute value of the determinant. So absolute value of the determinant of the following matrix. You write U and V either as columns or rows, doesn't matter. Okay. And you get a real number. So determinant itself is nothing but signed area. It can be positive or negative. And actually, in reality, we need signed area. Why is that? Suppose you want to measure how much, let's say, fluid goes through this page or air goes through this page. Suppose I don't have a physically, let's say, an area, but I have theoretically some region here and whether air flows, and you want to measure it. Some part of the air may go this way, but some other part may go the other way around. Therefore, you have to, when you are computing, okay, I have to stay here. When you are computing how much air actually goes to this side, you would like to compute it. The ones goes in and goes out. So you should use a sign, okay? And this is actually, determine gives you that gadget. This object, whether you take UV or VU, gets an orientation, and usually we denote the orientation by the normal vector to this plane. And in 3 space, normal vector is nothing but, you may take it this way, cross product. And determinant is actually just the length of this cross product also, right? It is just the length of this cross product. Okay, so so determinant is signed area, and a 2 form is a combination of those digits. Okay. Well, note that this expression determinant of AB CD is what? This is AD minus BC. We have so-called this objects dx. When you apply dx to a vector AB, okay, actually it may be ABC. Okay, let me say in R2, it gives us the first coordinate, right? dx. So this is A, and D, okay, x1, let's say. dx2 AB gives us the second coordinate. If I had 3 coordinates, if I work in R3, then I have also dx3 and so on. How would you write this expression? Well, I have 2 vectors. We have so-called an operation for this kind of objects or vectors, so-called tensor product. Okay. I will not go into detail, but tensor product is something like this. Suppose you have 2 vectors and you want to feed those 2 vectors into 2 linear forms, okay? Like this one. And if you have 2 vectors like this, the way this is defined as follows. The first guy, it's the first vector. The second guy, it's the second vector. So this is just dx1 u times dx2 v, okay? This is the definition. You may take it as definition of tensor product of 2 one forms, okay? What about this gadget? And if you consider this object dx1 tensor dx2 minus dx2 tensor dx1, evaluated on the vectors u and v. U is this vector, v is this vector. So what is the result? So dx1 evaluated on this times dx2 evaluated on this minus dx2 evaluated on this times dx1 evaluated on this. So what is this? This is just the first coordinate. So it is A, and then this is D minus second coordinate B, and then first coordinate C. Okay, so determinant can be written like this in terms of one forms. And this expression here is kind of long, okay? Short notation for this. Let me okay, change the board. Çalışmıyor neyse. Okay. We have a notation. This expression will be denoted as follows: dx1 dx2 minus dx2 dx1 will be denoted as dx1, we say wedge product, okay, dx2. So this is nothing but this expression, okay? Tangent space, yeah. Yeah, yeah, of course, yeah, yeah. Okay, so dx1 wedge dx2 is just dx1 tensor dx2 minus dx2 tensor dx1. This is true not just for one forms on R2 or R3, or it works for all n, okay? So I may have just not two coordinates, but I may have several coordinates. Okay. So in R3, you know, a one form is something like this. dx1, we have dx1, dx2, and dx3, right? These are kind of basis elements for one forms, and any one form is a combination of these, right? And any one form can be written as şöyle yazmıştık. Orada omega dedim. Gerçi kitap daha çok phi'yi kullanıyor, değil mi? Phi'yi kullanayım. F1 dx1, F2 dx2, F3 dx3. What about the form of a two form? Well, two forms is an object like this, dx1, dx2. In R3, I have also dx3. So I should also take that into account. So in R3, any two form has the form onu da nasıl gösterelim? Omega diyeyim. Şöyle olacak. F times dx1 wedge dx2 plus G times d x2 wedge dx3 and plus H times dx3 3 wedge dx1. Note that, you know, by the definition, buraya gelecek mi? Yok, gelmedi. Şöyle yapayım. Ha, biri bu algılanıyor. Note that, you know, so this is dx1, dx2. If I interchange 1 and 2, I will get minus of this, right? So this tells me that dx1 wedge dx2 is just minus dx2 wedge dx1, right? Because if you interchange 1 and 2, you get minus 1 times this expression. Exactly. So let me state that fact over here also. Bunlar tamamen kaymış. Okay. Note that dxi wedge dxj is equal to minus dxj wedge dxi. Okay. Anlaşılmayan bir şey var mı? Orada anlaşılmayan bir şey varsa hemen sorun. Yani basit şeyler ama hani anlamıyorsanız, burası hızlı geçti anlamadık derseniz durdurun hemen. Yeah, you have to fit two vectors to a tangent two form. So a two form, okay, a two form is a function omega. So at each point you have to fit two vectors to a two form. So it means what? You have TP, so you take union of this because you do this at every point, R3, at each point, and it gives you a real number, right? You give two vectors, it measures kind of the area of the parallelogram spanned by that, by those vectors, okay? It does it at every point, okay? You give two vectors at every point, it just computes you the areas, signed areas. Yeah, okay. Like you know, this one, they have to at you know, cover point. Like this. All right. Now we have bir şey daha söyleyecektim de unuttum. From this, of course, it is clear that note that this identity implies what? If I write I here, I will get minus the same thing. Therefore, right, if I have I here, I will have I also here. So the same thing, but same thing is equal to its negative. That is possible only if that thing is zero, right? So dxi wedge dxi is just minus dxi wedge dxi, and this implies that dxi wedge dxi is equal to 0. Of course, it is also clear from this definition, right? Neredeydi? Yeah, here. It's also clear from this definition. If you have the same object here, you will get 0, of course. This is determinant, so you should, it is linear in each coordinate, and it is anti-symmetric. If you change the vectors, you get negative value, right? Like determinant, if you change 2 rows or 2 columns, you get negative, -1 times the answer. So the same thing holds here. We have a proposition. Okay, I already proved some parts of this. Dx times dy minus dy x. Okay. Dx wedge dx is 0, or whatever that thing is, 0. If bunu şöyle yazayım. Buraya yazmayayım da başka tahtaya yazalım. The third one is the following. Okay. If phi is, let's say, some function times dx1 plus some other function dx2 and some other function dx3, and psi is one form, a times dx1, b2 times dx, and c2 times dx3, then phi wedge psi is what? Okay, let me write down the answer. A1 B2 minus A2 B1 dx wedge phi, doğru değil bu tabii ki, dx1 wedge dx2 plus A1 times C2 minus A2 times C1 dx1 wedge dx3 and A1 C2 minus B2 dx2 wedge dx3, and the last one is this. It can be seen from this, change the order of the product, you get it's negative. Okay. Well, we have seen most of them actually. Maybe I may do this in more detail. Proof of 3. So özür dilerim. Özür dilerim. Tamam. Sağ ol. Okay, let's see this. So it is just a dx1 plus no a b1 dx2 x3, which a dx1 plus b2 dx2 plus c2 dx3. All right, so what is the wedge product? So here I have a1 times a2, but then I have dx1 wedge dx1, that is 0. So I will not write that down. And then I have a1 times b2 dx1 wedge dx2, but then I have b1 times a2 dx2 wedge dx1. That is just the negative of this. Therefore, I write as b1 times a2. Okay, and the others are similar, actually. So a1 times c2 minus c1 times a2 dx1 wedge dx3, and then finally b1 times c2 minus b2 times c1 dx2 wedge dx3. Okay. And the fourth one is a consequence of, this property that when you switch dx and dy, or dx1 and dx2, you get its negative. Okay. Well, we have seen one forms, we have seen two forms. Now let's go back and let's think about zero form. What's the zero form? One form, it's right. If you are at a point and you have a vector, tangent vector, one form eats this vector. Two form eats a pair of vectors. Zero form, it will eat no vector. So it is just a function, okay? Function at this point, right? A one form is, some function times dx. Two form is some function times dx, let's say dy. Zero form is just a function. It's no vector, okay? So let me write here. Functions can as all right. Silgimiz. All right. Now I have a definition. Okay. This is called exterior derivative. In calculus, we know what derivative means. Differential forms are kind of generalizations of functions, right? They gives you some numbers at points, but they also takes values on the vectors, right? They take a value at the point and a value on the vector or pairs of vectors. So they are kind of generalized functions. And since we take derivatives of functions, we may try to take derivatives of form. And this is done actually as follows. So this definition, if phi, let's say, is a one form like this, as I said earlier, you don't have to go from 1 to 2 or 1 to 3. You may go from 1 to n. Everything we do here is specific to R2 or R3. Although we will study curves and surfaces in everything we do here, not everything, but things we do here, at least differential forms. So if I have a one form here, one form like this is a one form on R3. The exterior derivative of phi is defined to be the two form. So derivative of phi is defined this way, and it is nothing but the following. You take, so this is the function. You take the derivative of this differential. Its differential is a one form. So dfi, I have this one form, and then I take wedge product with dxi. Okay. This is the definition, but it has a motivation actually behind. You will see it later, probably. Why it is defined this way, and why this is the right way of defining derivative. Although it seems something very algebraic, this definition is very geometric. You also see that. Okay, let's do some examples. How one compute exterior derivative. Well, of course, you may ask what is the exterior derivative of 0 from 2 form. Let me also if f is a function, but is a zero form, in other words, a function, then its exterior derivative is defined as just df. Okay, the one form corresponding to f. Okay, exterior derivative is just df. And if you have two form, if let's say omega, let's say is the two form like this, f dx1 dx2, which g dx2 dx3 plus h dx1 wedge dx3. Aslında bunu şöyle yazmak daha iyi. Cevap daha iyi çıkıyordu ondan. Böyle yazmakla diğer türlü yazmak, şunun başına eksi getirip getirmek, değil mi? Hani başka bir farkı yok. Aynı şey de birinde eksi, öbüründe minus fonksiyonun. If this is a two form, on R3, then its exterior derivative is defined to be what? The tree form. So what's that? You just repeat what we have done for zero form or one form. You take the derivative of this, which, and then dx1, dx2, plus derivative of this, which dx2, which dx3, plus dh, which dx2, which dx3, which dx1. But then, of course, you will ask, what is the triple product, right? But that's also, actually, it will be clear if we think of the definition of or interpretation of two form in as what as determinants. So dx wedge dy corresponds to determinant of 2 by 2 matrices. Dx wedge dy dz will correspond to determinants of 3 by 3 matrices, nothing else. So here, here, let's say dx1, dx2, dx3 is nothing but the determinant. So when you compute this on, let's say, 3 vectors, v1, v2, v3, this is just actually, yeah, this is just v1, v2, v3. So these are just 3 vectors. You put them like this.
Tahtayı çevirmediniz.
Okay. So if you have 3 vectors like this, 3 one forms, and so this is a 3 form which will eat 3 vectors, and the way it eats 3 vectors is nothing but, you write these vectors as rows of this 3 by 3 matrix and take its determinant. The direct generalization of what's the, what a 2 form is. In terms of tensor products, we may write it this way. Okay, let's say this is A, B, C. Of course, technically I have to put P here, but for the time being forget that. Suppose I am working at a fixed point, and these are just linear transformations at that tangent space, and these are vectors at the tangent space. So I have a fixed point here, and I have 3 vectors like this. Okay, and these one forms, when you feed those one forms to these vectors, you will get either first coordinate or second coordinate or third coordinate, right? Depending on the index of the xi. And this gadget is what? This is just, so the definition is you write the first vector, A, B, C, and then let's say V2 is just D, E, F, and V3 is G, H, and K. So D, E, F, G, H, K, and you just take this determinant, okay? And it will turn out to be the following. It turns out to be just as in the case of wedge product of 2 one forms. This okay. So dx1 wedge, dx2 wedge, dx3 is just the following. So it is dx1 sadece 2 tane olsa, if I had only dx1 and dx2, it would be dx1 tensor dx2 minus dx2 tensor dx1. If you have 3 of them, it's like, the expansion of determinant. If you have a 2 by 2 matrix, you have 2 objects, right? A, B, C, D. So this is AD minus BC. But if you have a 3 by 3 matrix, then you have 6 terms, right? So this will be the same thing, okay? So this is just dx1 tensor, dx2 tensor, dx3. And then you just write down all the permutations of this. And whenever you switch 2 elements of this, you pick up a minus sign. So first, let me interchange these 2. So dx1 tensor, dx3 tensor, dx2. And then we have what? I may interchange these 2. If I interchange these 2, I will get another minus sign. So dx3 tensor dx1 tensor dx2. And then let me interchange these 2. So I get dx3 tensor dx2 tensor dx1. And then we can do what? Oh, okay. They are all tensor. I'm sorry. And then let's do what? Let's interchange these 2. So dx2 tensor dx3 tensor dx1. And then let's, efendim, bu artı olacak. Özür dilerim. Son olarak da şu ikisinin yerini değiştirelim, değil mi? So dx2 tensor dx1 tensor dx3. So you see, I have all the 6 permutations, okay? So a 3 form measures the volume, okay? Measures the volume. Determinant is the volume of the, evet. Okay, I'll come to that. So this is a one form, right? One form has parts dx, dy, dz, or dx1, dx2, dx3. So when you open this up, you will get dx1, dx2, dx3, and so on, right? That kind of expressions. So wedge of three one forms is this. Okay. Here, of course, you know, these are just coordinate functions. I may replace them by any functions I want. Okay. More generally, right? These are just some functions, but I may choose any functions I want. More generally, df one, df2, df3 has the same, you know, expansion. Değil mi? X'in f'ten ne farkı var ki? X de bir fonksiyon, f de bir fonksiyon. Tamam mı? Hı. Evet. O da tabii başka bir iş de. Aferin. Hı hı. Evet. Wedge product is associative, but anti-commutative. When you switch two of them, you get a minus sign. But it depends on what is the form. I mean, if it is a two form, you know, it means it has dx1 and dx2. So when you switch two form with another form, actually you will get even number of permutation transpositions. Each transposition picks up one minus sign, and therefore if you switch the position of a two form, that will not affect the sign because there will be even number of sign changes. Okay. For one forms, it is true. Maybe I may just, okay. Şöyle yapayım. On dört. Okay. So let's say omega is a two form, and let's say phi is a k form. Then of course, you know, this. Because you know, I have two one forms here. Each one will go over k forms. So when you take the first one form and pass it, you know, k steps, I will have minus 1 to the power k. But then I have another one. So it will pick up another -1 to the power k, and I will have -1 power to the 2k, so that will be +1, right? So okay, let me just. And if you have this, and if this is a one form, let's say f dx plus g dy plus h dz, then this expression is the same as this one. Okay, you can check this, because when you switch the order, this guy, if this guy goes from this side to this side, you will have even number of transpositions, and each transposition picks up a -1 sign. Okay, let's give a break. After the break, I'll give one more example and then another theorem. And yeah, I think I'll pass to functions now. Okay, let me stop.